back after lunch. I think there's a few stragglers that hopefully will be joining us soon, but we should crack on because for me certainly it's my last evening in Barcelona and I will be able to relax. So, but we've got two great talks before that. We're starting off with Vishu Mohan and Pietro Marasso from the Italian Institute of Technology, and Vishu is going to talk about combining past experience, imitation, and exploration to swiftly learn to use new tools.
Is the mic on?
Yeah,
I think it's on. Okay, good. So, thank you, Professor Prescott. So, to start with, I have this building to thank because it's from this building that the work that I present today originally started a few years back. That's why you see in the background some of the tools which are placed at different corners of this building. So, I mean, these are many tools which you will find in different areas of this building, and some of the tools we have never seen before, but even when we try to look at them, we can anticipate what are the kinds of movement we can do with it and try to reason about what is the consequence of performing actions on these tools. So, this is the basic area in which I will be speaking on some ideas. So, tool use is a sophisticated behavior highly evolved in primates. Generally, animals like monkeys, crows use simple tools to extend their physical capabilities. Mainly, it is extension of reach or amplification of force. But humans are unique in having established a culture which actively revolves around manufacturing, selling, and using tools. So, tool use basically is our gradual progression from acting on objects to acting with objects in order to counteract limitations imposed by our perceptions, actions, and movements. But there are three basic questions: what I can do with an object, what is the consequence, and will it help me realize my goal? But in addition, humans are very swift in learning a large number of tools. I mean, I'm not speaking about divine skills like dancing or which may take years of practice. I'm speaking about the common tools which are found in a domestic environment or industrial environment. And we often use multiple techniques to learn. We learn by observing someone else, we learn by physical interaction with the tool itself, or we remember some similar experiences from memory and try to use it to our advantage. So, while working with the humanoid robot iCub, I just tried to ask this question: how multiple learning streams can be combined to swiftly learn a new task. And the second question which I added was, what is the recipe to learn green? Or how can the knowledge be recycled? Today I learned something else. How I can use it to learn some other skill tomorrow? So, what is the recipe to learn green? So, these are the two important questions which I tried to address with this work and the other kinds of skill learning tasks that I'm trying to do with the robot. So, this is a short outline of the rest of the talk. So, I'll speak about the scenario, what is the building block, what is the basic idea, the how part, and some questions. So, it's fairly simple. So, the new task is the task which I'm going to speak about today. So, the task is basically to learn to bimanually coordinate a toy crane in order to basically position the magnetized tip at a goal which is unreachable to the robot. So, what I'm trying to use is the complete 35 degrees of freedom of the robot, and the goal is to combine three different streams of learning. One is the past skill of learning to scribble, or I don't know if I can switch on the video. Yeah. So, what I like about this task is that it doesn't stop with one demonstration, but the teacher basically produces demonstrations of increasing orders of complexity. For example, like this, I see a shape like this and go on. So, and the robot has to use the past experience to gradually synthesize more complex trajectories. So, try to learn this new task using, first is the previous experience, second is some demonstration by the teacher, and physical interaction with the tool itself. So, this is the scenario I want to speak about today. So, the building blocks, there are many building blocks which are needed to start this task itself. Some are related to perception, some are related to action, recognition of movement of the teacher, and so on. But one of the building block which is crucial is the system which coordinates the upper body of the robot, and is called as the passive motion paradigm. And it's currently being used in a number of European projects for a number of reasons, but I won't go into the details. It's a framework which is inspired by the equilibrium point hypothesis and the theory of impedance control. It's useful for 4 reasons. One is generation of action in highly redundant system, compositionality, taking into account multiple task-specific constraints while you are performing a movement. It acts as a core module in skill learning, and it's also used in mental simulation of action. That's where the PMP diverges from the equilibrium point hypothesis. So for people who are more interested, there is a recent review paper on the model which I wrote very recently. So in the context of learning to use the toy crane, you need something which will allow the robot to bimanually reach the toy crane with a particular wrist orientation and grasp it. And second, you need something which will generate the motor commands for the upper body during both explorative interaction and goal-directed coordination of the toy crane. So these are the 2 things for which you need this model. I'll have just one more slide on the PMP, because this is the slide which I'll use in the last part of my presentation also. So the first is the metaphor, and the second is the network implementation. There are many metaphors to explain this model, but the most recent one is the conversation between the dancer and the dance teacher in the movie The Black Swan. So Nina says, "I'm perfect, while the dance teacher says, perfection in movement is not to be in absolute control, but to let go the body to the forces of nature." So this is the puppet metaphor of the PMP model. So as the goal pulls the tip towards the target, the rest of the body elastically reconfigures in order to allow the highly redundant degrees of freedom to reach the goal. So in terms of the network implementation, it looks like a complex network, but there are some regularities which can simplify it. So there are some points which I want to speak very fast. So these networks are assembled on the fly. So for example, this is a network for bimanually coordinating the steering wheel of a car. So the first thing we should note is that there are many ways to represent the same action. I can represent the same action using a monodimensional steering wheel pattern. I can represent the same action using 6-dimensional end effector space pattern. I can represent the same action using 7-dimensional joint space pattern. So there are many equivalent ways to represent the same action. And what this network tries is to incrementally derive motor commands in all the intrinsic chains. So there are multiple motor, so based on the task, there are multiple motor spaces. In this case, this is the tool space, which is the steering wheel. This is the end effector or the hand space. This is the arm space. This is the waist. So waist is grounded in this case because you are sitting and driving the car. So if you're using the lower limbs, then the ground changes. So every motor space just consists of 2 nodes. One is the position node, and the other is the force node. And there are 2 kinds of connections. One is the elastic connections, which are the stiffness or the admittance matrix, and the horizontal ones are the Jacobian matrices. So horizontal ones map the geometric relationship, while the vertical ones map the elastic relationship between force and between multiple motor spaces and force and position nodes. So there is also an element of circularity in this network. Every node is connected to every other node, and goals can couple at any point in the network. So it's a multi-referential system of action generation in which multiple constraints can be taken into account at the same time. Okay, and there is an element of directionality also. The directionality is constrained such that every computation is well posed. So there is no inversion that is taking place in the model. All the computations are local and well posed, so you don't have to invert a highly redundant system. So now, if you don't want to, so this is just the network for coordinating the upper body. So I just removed the tool space. If you don't want to use the waist, just reduce the admittance at the waist space, and you just use the upper body. So the many other degrees of freedom can gradually get coupled while solving the task. So if the target is unreachable, I also use the degrees of freedom of the arm and the waist or the lower limbs and so on. So you can incrementally recruit degrees of freedom to generate an action. The final slide, you can also impose multiple constraints. As I told, goals can couple at any point in the network. And as the disturbance is circulated cyclically around the nodes, the rest of the system basically reconfigures in order to take into account multiple constraints. So in this case, what we have just done is try to reach the toy crane with appropriate wrist orientation, taking into account all the joint constraints, internal joint limits, and so on. So it can be used for many other tasks. Like for example, this is playing with mechano tools. So these are for 2-year-old children for simple assembly tasks. Okay. And the graph here shows just a simulation on a 3 degrees of freedom arm. Well, this is the total upper body of the robot. Now the core idea. The basic idea behind green learning of tools was the introduction of the notion of shape in the domain of movement. So shape is generally considered to be perceptual, visual, or haptic in nature. So what we tried to do was introduce the idea of shape in the domain of movement and how it can be useful for skill learning and recycling of skills. So you learn at a more abstract level. So this was the basic idea. So I'll just give a very simple example. So trajectory formation is one of the basic functions of the neuromotor controller. So while performing actions with many tools, we often synthesize a wide range of movement trajectories. So by moving from trajectory to shape, the advantage is that it's possible to liberate the trajectory from task-specific details. Now I am only speaking about the trajectory because the degrees of freedom problem is already taken care by the passive motion paradigm. So now I am just speaking about the movement trajectories, that's at the end effector space. Okay. So by moving from trajectory to shape, it's possible to liberate the trajectory from task-specific details. What are the task-specific details? Who did the action? Did my right hand do? Did someone else's leg do the action? Where did the action take place? Did I write a U on a piece of paper or run a U in the playground? When did it take place? And so what? What is the consequence? These are things which can be combined at a later space. So at least while learning in an abstract way the motor skill, I wanted to remove all these task-dependent details. So what is shape? That's the next question. I just give a very simple example of U. So the essence of a shape, a trajectory like U, is the presence of 2 endpoints and minima in between. Now, once you can capture this essence, whether it's the U is drawn on a playground or on a piece of paper, what is the scale, it does not matter. And then you also have an element of compositionality. You can compose these simple shapes to generate more complex shapes. For example, this is a sketch of a side view of Gandhi, if you look properly. So there are two things, towards context-independent motor knowledge and towards context-dependent motor action. So this is the inverse problem. So instead of teaching a robot to synthesize movement trajectories and then going to the degrees of freedom problem and so on, if we try to instead teach it to perceive and synthesize shapes, then we give it a graphical grammar to basically learn a wide range of motor actions based on context. So this was the core idea. So context-independent motor knowledge and task-specific compositionality. How do you bring these two things together? And the basic advantage of learning any skill or in an abstract way is that it allows you an implicit potential to perceive, mime, and begin to perform many other actions that share a similar structure. So, and if you try to analyze the basic tools or scripts, there are very few shapes, even though it's required to generate a wide range of trajectories, it boils down to very few simple shape features. There are 12 of them, but of which I think 3 of them are more important, which is the line, bump, and the cusp, as I call them. And so I just put a slightly more complicated cartoon of the computational loop itself. So you start with a demonstration. From the demonstration, you basically extract the shape of the teacher's trajectory. For this, we use the catastrophe theory. It originated from Thom, and so what you get after shape extraction is basically a discrete set of critical points, as I told, for U or O or more complex shape. So this is called as the abstract visual program. Now these trajectories are observed by the robot through the vision. So you need to basically reconstruct it in the egocentric space of the robot itself. So this is done by a 3D reconstruction system. So what you can do in this loop is basically move from the demonstration to an abstract representation of the demonstration in the egocentric space of the robot. Now comes the inverse problem, which is converting a discrete set of critical points into a continuous sequence of equilibrium points, which can act as an attractor to the body model of the robot. So now here is the trick. So what we did was, how do you learn these things? So what we did was, exploit this element of compositionality. So if we just learn the primitives, then you can compose, from the learned knowledge of the primitives, you can build more complex actions. And what we showed was that to learn the basic shapes, it's very easy, just by changing the stiffness and timing. So these are the parameters. For one set of stiffness and timing, you get one trajectory. For something else, you get some other trajectory. So learning the primitives itself is very easy. And once the primitives is learned, more complex actions can be represented as compositions of these primitives. So once you get a virtual trajectory like this, then you can use it as an attractor. So the puppeteer is pulling the puppet in a specific fashion. And the PMP takes care of the generation of the movement of the robot. Now, how do I get the shape of my own movement? So for this, you use the output of the forward model. So when I'm moving, I also have the efference copy of how I am moving. So just okay, good. So I use the same computational system to both extract the shape of the teacher's movement, for which I use vision. And in this case, I use the output of the forward model to extract self-generated movement. Now I can compare the shape of the teacher's movement and shape of my own movement and just close the loop of learning. So this was the complete computational loop for perception and synthesis of movement shape. This is the last part of my talk. So on the role of multiple learning streams while for a new task. So in this case, what I have is the system is disconnected, and I have a model which coordinates the upper body. The tool space is represented exactly as any other motor space. So during coordination, the distinction between the tool and the body is blurred. So what you have to learn is the interface between the body and the tool, or the consequence of my movement and the resulting what happens on the tool. So my movement to what is happening at the tool space. If you change the tool, you just have to change the interface. So you can load it from the procedural memory, and so there are many ways to learn the interface. The first is the normal: generate a set of motor commands, observe the consequence through vision, and what you get is two streams of data: motion of the two hands and the motion of the tool tip, from which you can learn this geometric relationship between my movement and the movement of the tool. The second way to do it is by observing the teacher. For example, the teacher shows how to use the toy crane. Now, by using the computational loop for perception and synthesis of shape, you can basically use the ingredients necessary to generate this kind of curved shape, which result in bump critical points, have already been learnt during the past experience. So now what you do is, since the teacher is moving like this, you start with a plan, send the plan through the network, take out the motor commands, and replay it on the robot. So in this way, you can replicate the demonstration of the teacher. So once again, you get the same stream of data. And once you get this, you can train a very simple, this time I used a very simple network, and from the connectivity matrix of the neural network, you can take out the Jacobians. So once the Jacobian is learnt, the network is, before that I just want to summarize. So what I did is, teacher's demonstration constrains the space of exploration. Past experience gives the appropriate parameters to swiftly imitate the teacher's movement. Practice generates self-relevant data that helps you to learn the geometric relationship between the body and the tool. And once the network is complete, the PMP mechanism helps you to generate goal-directed body plus tool actions. So this was the complete summary of the whole loop. So I think here, so this is the, once you learn the tool Jacobians, the network is complete. I'll speak something about the tool admittance in the graphs that come, but I think there was a video here. Okay. I don't know. This is one example of trying to reach but okay. So now, before I conclude, I just want to present 3 graphs. So the first is the normal condition. In the normal condition, both hands are actively functional to generate force, and so the tool reaches the goal target. The forces exerted by the 2 arms are almost bell-shaped and converge at null values. The tool torque and the tool velocity is also bell-shaped. So in this case, I mean, the goal is achieved. Now what I do is, I make the right arm dysfunctional. So I can do this by reducing the stiffness of the right arm by 10 times compared to the left arm. Now what happens is, despite a very different force profile of the right and the left arm, the tool tip still behaves in a very consistent way. It tries to reach the target. It's not completely reached. The tool torque is also approximately bell-shaped. And so for this, no learning is needed. It's the property of the attractor dynamics of the goal-directed body plus tool network to take into account. So if my right arm is not functioning, you can also see that the left arm is delivering more force just to push. So there are 3 things. Modularity helps to restrict the damage. Redundancy helps to stage a cover-up. And attractor dynamics ensures a graceful degradation of performance. So the last graph is basically, after we did this, many people asked me, what about the tool admittance? What do you do with the tool admittance? Is there a learning? But so the tool admittance can be controlled during the design of the tool itself. For example, we apply lubricants on steering wheel to make it more compliant. But during goal-directed coordination, the only way you can act on it is apply more force. So I asked this question, what if the toy crane was not a toy crane but a human being instead, who chooses not to comply? How will the resulting dynamics be? And this is quite relevant because if it is an inanimate object, if I apply a force, it has to basically comply. And but living machines at least have a choice to comply or not to comply. And so this can be done by making the admittance of the tool space too low. So it doesn't comply to the force generated by the robot. So in this case, what you see is something very nice actually. So in this case, if the tool is very compliant, you see something like this. Everything is fine. The 2 systems, the body and the tool, are cooperating and the goal is achieved. In this case, the goal is not achieved, even though the PMP based controller is trying to persuade the partner to cooperate in the goal. But despite the persuasion, there is no cooperation in the achievement of the goal, so the goal is not achieved. And what you also see is there is still some energy circulating in the network, which could not be channelized in the achievement of the task itself. So this, in negative terms, it may be considered as some kind of a frustration which may reduce the tendency towards cooperative behavior, and learning. So this was so there are three cases. One is the normal case, the second is the pathological case, and the third is what if the toy crane was not a toy crane but an animate being which chooses not to cooperate. So in all this, what does PMP do? So there are many things which has to be learned. One is the stiffness and timing, which is for the shape and spatiotemporal trajectory synthesis. Then there is a geometric relationship, which is the horizontal connections. How internal joints are coordinated, which is the posture. And PMP is a kind of a box where all these ingredients are combined to come up with a recipe. So so we are trying to use this approach for some other tasks related to tool use and for assembly, industrial assembly operations. So there are three questions which I tried to address in this talk. The first is the body, or goal-specific coordination of a highly redundant body, which is the passive motion paradigm. The goal being a skilled puppeteer who composes and recycles. And the final question is who pulls the strings? So who is the one who exerts the force? Who is the one who complies to the force? So which is the third graph which I showed. So before I end, so now at present I have tried to take a break from the PMP model, though it plays an important role in many things I do. So right now, this task is very inspired by the shape work. So it's a very simple task, learning to build the tallest stack given a random set of objects. So instead of doing motor learning and skill learning, this time I want to focus on learning the properties of objects and relationship between properties of objects. So what is nice is that the problem cannot be defined itself, because you do not know which object is going to come in front of you today, and in combination of which other objects is going to come in front of you. So it basically requires a gradual episodic interaction and digesting this information. So it's something which I try to focus on these days. So to conclude, in this kind of learning tasks, you can enter into environments where you know partially something. There is a lot of things which are not known, which is the novelty and the combination of elements that come in front of you. And you have to just learn to keep the best foot forward to survive. So this is the complete essence of what I'm trying to do with the robot now. So I just want to thank some of my teachers and the projects which fund such kind of work. Thank you.
Great, well, that's a fantastic talk. And questions, please.
Unless I misunderstood you, I didn't see any sensory feedback, any perception in your scheme.
Oh, vision. Mainly vision. Mainly vision and proprioception, vision, proprioception.
Also using but what about how would including tactile perception help achieve?
Tactile perception in this case can help in basically grasping, knowing that I'm in contact of the object, but the rest is force and torque. So we measure the force, we measure the torque, you get visual feedback and the forward model output. But tactile can be useful in the other task, which is pushing. Because when you push an object, you have to be in contact, otherwise you cannot push it. So this is another task where I realize the importance of tactile. Even if you try to push and pull with a tool, we know from animal studies that if the object is placed here and the tool is somewhere here, it doesn't act, because it knows that for pushability you need contact. So these are the kinds of tasks in which tactile can be more dominant.
And it would fit naturally within the scheme that you were putting forward.
Surely, surely. For some tasks, some parameters are dominant, and it's up to us to learn which is the causally dominant parameter or the ingredient in.
Any questions from the back? Could you say a bit about extending it to many different effectors? If I've got lots of manipulators and I wanted to use them at the same time.
Effectors means?
Arms, sort of octopus.
Yes. This is a network model of action generation. So it does not matter how many effectors. For example, right now you have two. If I had a third arm, I could still connect it and.
So it will scale just.
Oh, it will scale because all computations are well posed. There is no inversion or anything. So it does not matter what is the intrinsic degrees of freedom that is being coordinated.
But
so
when they act together on objects.
It depends on who is pulling the. So what is the internal degrees of freedom does not matter. But coordination of multiple arms requires planning at a slightly higher level, because if I am trying to do this, then both hands have to be coordinated in space and time. So this takes care of the movements at the intrinsic joint level, but this requires also temporal, and because if I miss in time, it is going to fall down. So these we have done bimanual transportation of objects with the model. With two arms, it seems to work very well. So.
Okay, thank you very much.
Oh, yes.
If you can put it inside.
Yes.
So our final talk for Living Machines 2012 is, we're delighted to have David Lanting, who's moved around. He's now at Stanford, that's right, and was recently in Belgium. Is that right? Netherlands, sorry. And last year was at the BCPT, and just I think this year's moved to Stanford. And in the Netherlands, he was making a huge impact with his science and won a number of rewards. And I'm sure he'll continue to do so now that he's moved to Stanford, and we're delighted to get him back into Europe to address this Living Machines conference. David's work covers many different kinds of living machines. Particularly, I think we're going to hear about plants and also birds today. So I'm really looking forward to it. Thanks, David.
Thank you, Tony. Thank you, Tony, for inviting me, Paul as well. And thank you all for staying till the last presentation. It's a pleasure to present for you all. And it's also a real pleasure because I really love studying the biofluid dynamics of flight. And one of the reasons is because it's such a nice inspiration for design. And these are just a couple of examples of student projects I will talk about. Well, if you think about flight, and if we are inspired by animals, we have to think about insects, because insects were the first 350 million years ago to take off from the ground. And, well, the true flies are perhaps the most accomplished flyers. They have a single pair of wings, and they have a very powerful wing stroke. And, yeah, they have some truly amazing flight behaviors. So as you can see, flies can fly really well. And what this illustrates, it illustrates an interesting question about flight, because according to aircraft theory, which was revolutionary 100 years ago, when we actually evolved ourselves to take off in the air with our aircraft, that theory cannot explain why flies fly. So you guys might think, you know, and you're right, a fly cannot lift a frog, but according to theory, there's also some problems with the fly lifting its own weight. So it's a nice example to get you started in thinking about how special insects fly. And one of the discoveries of how this actually works was made with the hawk moth. So there was this hypothesis of Max Worthy in the Journal of Fluid Mechanics in the 70s. And he said there was some sort of separation bubble. It was a hypothesis. So he wasn't talking about a vortex, but a separation bubble, but a recirculation of fluid. And basically, Charlie Ellington and his colleagues at Cambridge University in 1996 in a Nature paper, they discovered that it's a vortex. It's a tornado-like vortex that runs parallel along the leading edge of the wing. And well, what it does it actually lowers the pressure on top of the wing, which helps suck it up, and that actually helps insects achieve that miracle of flight, where they generate 50% more lift than predicted by simple aircraft theory. So, but one of the questions that I started to think about when I started studying insects is, why does this vortex stick? This is a stable leading edge vortex. Well, think about the motion of this wing, right? So the wing is going back and forth like this. Why doesn't the vortex get blown off? And that's actually a complicated question for a couple of reasons. Well, you have insect flight behavior, you have wing morphology, you have diversity. There are like 1 million species of insects. So there are a lot of different ways to look at this problem, and you have to integrate a couple of them at least to get a better perspective about it. I think that's what's exciting, and that's why I ended up in this field. So what I'm really interested in general is what the interplay is between Darwin's theory of evolution and Newton's law of motion, and how that shapes locomotion in nature. And I think that comes together because if you look at biology, there's so much diversity, you really have to focus on a few species to start with and find some really interesting key questions. Because if there are 1 million species, you know, we cannot study them all during our lifetime. So it will take a long time to see them all. So you need a bit more advanced approach. And what's helpful is if you use engineering methods to make measurements. Because I think one of the challenges in biology is that, and sometimes biologists seem to forget this. I have been teaching mathematics to biologists, and I taught them when they're in the second year that they had a wonderful, wonderful topic and area of research. Because I, as an aerospace engineer, that's how I started out, was in this really simple field where we're just playing around with aircraft and we could actually make some decent predictions. Whereas in biology, you need the best math, the best engineering, and then still, most of the time you're failing because there's so much still to be discovered. So that's why I think it's really exciting. You need good methods, and new ones help. And then finally, if you understand how something works in biology, it can give inspiration for new ideas and designing novel microwave vehicles. So that's why I'm in this game, and I really enjoy it. So the biofluid dynamics of flight as an inspiration of design. So now let's get back. So when I started, I was lucky enough to start off with Michael Dickerson at Caltech. And I started thinking about how fruit flies fly. And he solved a very interesting problem. Here you have this fruit fly. It weighs just 1,000th of a gram. It has a size of 5 millimeter. And if we want to go back to this question I posed initially, like why does this vortex stick to this flapping wing? Then there are some problems if you want to study that for a fruit fly. So how do you measure the flow and forces around a fruit fly? It's very tiny. It weighs almost nothing. There are not many sensors that can accurately measure 1,000th of a gram dynamically, right? That's really challenging, let alone just that force. So something needs to be done about that. And then what I was particularly interested in actually was find a mechanism that can explain the stability of the vortex. And so to do that, to understand that mechanism, I actually used the Navier-Stokes equations because I'm an aerodynamicist. I like equations, I like fluid. And so if you look at a flapping wing, there are actually 3 wing motions. So you have stroke, is this one. Oh, I'll make a couple of them and say there's a stroke, is this motion. You have deviation, the wing goes a bit up and down, not too much. So this is the actual shape of the wing path. And then you also have wing rotation, right? So that's the last part of the motion. So there are 3 velocity components. And what they do is actually, you have a surface with a really complex boundary condition, a time-dependent velocity boundary condition. And the surface is moving through space, so how are you going to analyze that? Well, one way to do it, and I must admit it's in some ways simplistic, other ways it's a bit advanced. Well, you use the Navier-Stokes equation, and what you do is instead of using your reference frame on Earth, right, you take the reference frame and put it on the wing. So basically, you're putting a camera on the wing, and you're moving with the wing to watch what's happening with the flow. And that's not a really weird approach, but because that's kind of how we study, for example, cars in wind tunnels, same for aircraft. We make the air move so that we can study the flow over the wing. And you do the same with helicopter blades and wind turbines. So to analyze the flow over the wing surface or over the rotor blade, you actually attach the reference frame. And if you do that, you can see what happens with the air that flows close to the surface. It's actually going through quite complex motion because it has to track the surface. There's this non-stick, like there's this condition that the flow needs to stick at the surface. So it has to follow the complex movement of the wing, and that introduces some extra accelerations. And they go into the equation through the velocity u. You get these wonderful extra terms, and they're really nice because they do give some insight. What they show is that there are some acceleration due to flapping. So that's just moving back and forth like this. So that's really key. Whenever we think about flapping, we're thinking about this acceleration, moving back and forth. And so that's actually just going back and forth like this. And then there's another one, because the motion is a bit more complex. At the same time, while moving back and forth, the wing's actually also revolving around the hinge. So a bit like a propeller blade. And that also gives an acceleration. And this is actually Coriolis acceleration over there. So that's the Coriolis acceleration. And this is centripetal acceleration. And that really has a big influence potentially on the aerodynamics, besides this acceleration over here. And we would like to know, how big are these accelerations? Are they really important, yes or no? Well, to do that, to look at that, we use dimensionless numbers. You must all have heard once of the Reynolds number. It's really important in flight and in swimming and stuff like that. Well, the Reynolds number here, I changed it in my experiment that I'm going to discuss, from 110, which is relevant for a fruit fly, to 1400, which is relevant for a housefly, to 14,000, which represents a hummingbird. So that's a number that we're changing, and ideally the results don't depend on that number. That would be nice, because then we have something that's more general, that goes beyond for example, this fruit fly. And then we would like to estimate how big these accelerations are. Well, we can also get the dimensionless numbers for those, because this acceleration here, the flapping acceleration, actually is proportional to the inverse of the dimensionless amplitude, the amplitude A divided by the chord length C of the flapping motion. So, and that kind of gives the order of magnitude. The order of magnitude is roughly 1. And now if you look at the other type of acceleration, so the acceleration due to revolving motion, we find actually that's proportional to the radius divided by the chord length. That's also of order of magnitude 1. And the way to interpret that is like that radius divided by the chord length. You might have heard about the wing slenderness. Well, this is the wing slenderness with respect to the center of rotation. That's all. So compared to the hinge here, this radius divided by the chord length. It's important. The traditional way of looking at wing slenderness is from tip to tip. So, but in this case, this acceleration depends on this slenderness. And the question is, of course, which one is more important for leading edge vortex stability? Well, we don't know, but they seem to be of the same order of magnitude, so potentially they could be equally important. But it would be interesting to find out if that's really the case. And to test that, I use a robot, and this robot has been developed by Michael Dickerson at Caltech. And here you see it. It's submerged in a tank with oil. I'm releasing air bubbles at the leading edge and the trailing edge. And while it makes the flapping motion of a fruit fly, you can see this beautiful leading edge vortex stably attached to the wing. And what's so great about this robot in a tank of oil, what's so smart about it is that it's not only a way to visualize the flow or stuff like that, it's actually a gigantic force amplifier. The force is amplified with a factor 40,000. So per wing, we are now measuring 20 grams, and 20 grams is within reach of normal sensors. So that's what's so smart about this setup. Whereas the Reynolds number is completely the same, and it has to do with how the viscosity and the density are scaled to the same Reynolds number, but because of the big density difference, this works as an amplifier. So this is a really helpful device, and you can measure the forces generated by it if you make the wing flap like I showed. And also, shall try to illustrate it here. So horizontally, I plot the drag coefficient. Actually, it's a drag averaged over one wing beat, and then I made it dimensionless. And the same here with the lift coefficient. So the lift averaged over one wing beat, and then I made it again dimensionless. And the wing beat is from here to here to here. So, and then the average value. And then the different points in the polar represent different angles of attack at which the wing can flap. So over here, it's actually flapping at 0 angle of attack mid-stroke. So the wing starts out like this, and then mid-stroke, it's actually 0, and the angle of attack with respect to the flow is actually 0, and then it goes back like this, and then it goes like this. So this is the flapping motion that we're looking at. We could increase the angle of attack, which is much more representative, like in compared to fruit fly. That's what it's indicated here. Here we have 45 degrees, and it's more like this. So there's a big angle of attack mid-stroke. And then you get a lot of lift, which you see, that's actually the maximum lift. But you also get this nice, stable leading edge vortex. And you could even go and make a motion like this, just going back and forth like this. So we do the whole range of motions and look at the vortices and the forces. Well, now it would be interesting to understand which acceleration is actually more important, right? And we have these equations, and wouldn't it be nice if we could get rid of some of these accelerations, so separate them out in some way? And if we would start out, it would be nice to look at, well, the acceleration due to flapping, because if we're talking about flapping motion, that seems to be like the key motion that could explain leading edge vortex stability. So let's get rid of that term. Can we do that? Yes, we can. And the way we do that is by changing the kinematics of the wing. And I'll illustrate it with this model here. So this is a fruit fly flapping back and forth like this. And what I now do is, it's actually flapping back and forth like this. What I now do is I extend the wing, but I keep the actuator disc area, the Reynolds number, and the flapping amplitude constant. So I'm going to extend the wing, move it outward like this, and flap like this. And now you have a translational component and a rotational component. And if my arm would be infinitely long, the wing would actually just go back and forth. And it looks like this. And while doing that, we get rid of this revolving motion, and so we end up with only flapping motion. So the wing just goes back and forth like this. And we can look at the flows and the forces. I'll show that. I attached the camera to the wing, and we're just following it. It's flapping back and forth. We get this big vortex. It actually grows bigger and bigger. And just before it separates, the wing reverses and flaps in the other direction. But definitely the structure of the vortex is very, very different. It just grows, grows, grows. It's not really tight. It's not a spiral. So if we now look at the forces, right, this is what we got for the flapping wing. What do we get for, what sort of polar do we get for this translating flapping wing, right? And what we see is actually the forces go down. And also the vortex becomes wider and less stable. This is a nice result, but it's not completely convincing yet, right? Maybe we could just eliminate, for example, this flapping motion and just look what the revolving motion does. That would be really neat. And what we end up with is a propeller. It's just doing this constantly, right? And then we only have that acceleration. And let's look what happens with the vortex. What you can see is that there's a nice stable leading edge vortex, and it remains stably attached. The size doesn't really change, etc., till we stop, and then it washes away. What do the forces look like? Well, if you look at the forces, then actually we find, again, very high forces. Same order of magnitude, only less drag, actually. The drag is lower, the average lift is equally high. But then the question is, okay, this could still have to do with the shape of the wing or something else. So to really test if this acceleration is important, let's get rid of it. Can we do that? Yes, sorry, that's the wrong button. Yes, we can do that. We can get rid of it. And the way we do that is we stop revolving it. We just translate it like an aircraft translates its wing. That's all we're doing. And if you look at the vortex that arises, there is a vortex, look, a really nice one. It's a startup vortex, but then it washes away. It's get blown off the wing. And so this is a big change. And if we now look at the forces at the same time, and we can do this gradually, right? I did this in steps. But you can see that for this extreme case, which is plotted here, the forces really go down with a factor 2. And that kind of explains to you why normal aircraft theory, which is based on the aerodynamics of this wing, cannot explain why insects can fly, whereas a revolving wing can. It's an important model. It's the quasi-steady model of insect flight. And it also shows that revolving, the rotational acceleration, so the Coriolis acceleration and the centripetal acceleration are really important for leading edge vortex stability. So, you know, we only looked at one species. That's what's so nice about if you have a number, you can compare different species. You can compare how this R over C value, which actually determines how big this acceleration is, this rotational acceleration, how this compares among insects. And if you look at the average value, it's pretty much the same as a fruit fly. And like I said, I repeated these experiments at different scales, right? And I'm going to talk about that. But first summarize this. So what stabilizes the leading edge vortex on insect wings? They are stabilized by the rotational accelerations, so the Coriolis and the centripetal acceleration. And this can give some inspiration for designing micro-air vehicles. And why? Well, I repeated the experiments at the scale of a fruit fly, a house fly, and a hummingbird. And let's look what happens. So here we have the fruit fly, and I get this force polar. And the star actually indicates what the fruit fly does. It's the precise kinematics of fruit fly, and it's very close to the polar. And I repeated the experiments at the scale of a house fly, and I also repeated them at the scale of a hummingbird. And you see a small step, because the flow becomes much less viscous from here to there, but then it's almost an identical polar. And what this tells you is that the aerodynamics doesn't really scale, it's just constant. And what's so interesting about it is that many people they're thinking about structures, oh, that's easy, electronics, oh, that's easy, but aerodynamics, ooh, scary. Well, this tells you, once you figured it out at one scale, it will work at another scale. And that's really exciting design idea, because that really helps you solve a problem. You don't have to build a really small micro-air vehicle at the scale of a fruit fly to prove you can make something at that scale. And that's kind of like how I started out the design project with bachelor students. 10 bachelor students got 10,000 euros to design a flapping micro-air vehicle that can fly like an insect. And this is the result. It actually works. Here's another image of it. That's the improved design. And it can take off and land vertically, like an insect can. But it can also fly very fast. And it can do this often. So I speeded up the movie so you can see it fly fast. But at the same time, it could do this. In this instance, it did it like 18 or 19 times. So it can take off and land vertically, and also it can actually fly like fast normally in a normal mode forward, not like I faked it here. But that's what's so exciting about this micro-air vehicle, and it's actually not that expensive, and it's scalable. And so when we designed this version in 2006, my Japanese colleagues actually copied it directly, and I was very happy to see that they were able to build a first insect-sized flapping micro-air vehicle, which actually flies. All these micro-air vehicles fly. And it shows that you can scale design. And there was a hobbyist, so it's not a scientist, but a hobbyist in Japan who built a smaller version, so that's 6 centimeters and just 1.5 gram. And then there was a student in America. His name is Brian. I found him on the internet, and he built a 0.9 gram version. And it's still the smallest flapping micro vehicle that freely flies that actually works to date, to my knowledge. So, and it shows you that, once you have something that works, you can scale it down. And so what's the limit? Well, I don't know. There are many good researchers around the world trying to get smaller and smaller. Here's some inspiration. I figured it would be cool to film the smallest insect that can fly that I can get my hands on. Turns out to be a parasitic wasp of 1 millimeter. And here it sits on some butterfly eggs because it's a parasitic wasp. And so it needs to get to the eggs. And so the way it does it is by hitchhiking on the butterfly. So this is just for scale. And this is a short movie. This is, of course, in a test tube in my lab, which is very big for this small fly, or wasp. So This movie is also a bit for entertainment, of course. This is like 1/10 of a second in the life of a parasitic wasp. It was filmed at 22,000 frames per second, most of it. And if you want to see more movies, you can go to that website. I have a lot of free movies there that you could use for your teaching, and I'm hoping to update that over the years. And I will talk about it later. I put in some entertainment as well, because this is the last presentation. So you notice that I'll have a nice movie here and there, just to help you get through it. And also because it's fun. This is really the part where I get my inspiration. So we talked about inspiration for designing novel micro-air vehicles. And we were talking about scaling. And if this is a scalable effect, that suggests that the leading edge vortex, and I was working on this a few years ago, could be generated by many other species in principle. So, and to look at that, and to see if this is really a convergent solution in nature, we could plot the same number for different species, right? So here are hummingbirds. Hummingbirds are there really concentrated, and here are bats, and there are all the other birds. And what you find, like I said, birds, a lot of birds don't have slender wings. People always think of albatrosses, but think of small birds flying in your backyard. They actually don't have very slender wings. Compared to the center of rotation, where they flap, it's not really slender. And so, in principle, they could all generate this stable leading edge vortex according to my results. And they also all have, like on average, have an R/C value, which actually is the Rossby number, which is really close to that of fruit flies, which is kind of funny. Like they're all kind of close to each other. There's a lot of diversity, but on average, it gets close to this number 3. So let's keep that in mind. And now let's look at hummingbirds in the middle. They're in the middle of a bow tie, and they're really cool birds. And I feel really lucky that I'm in California, not only because I'm in a great place, but also because they have hummingbirds, which are my favorite birds. So I've put up my hummingbird feeder after 2 weeks, of course, when I arrived, and I have now lots of friends, all nice hummingbirds flying in front of my house. And basically, here I looked at, in total, actually 13 species, but this shows the diversity of hummingbirds. And the challenge with hummingbirds, if you want to understand their aerodynamics, is that they're really small, lightweight birds, around 3 grams, 1.5 gram per wing. So the minimum drag per wing is around 0.1 gram. How are you going to measure that? It's complicated. You cannot build a model wing in oil because these are feathered wings. That's not a good model. It's much more complicated. So the first attempt to measure the forces of a hummingbird wing was for a spinning wing setup with hummingbirds, and it was actually made by a friend of mine, Douglas Altschuler, and he used to set up in Cambridge, but it was a challenge. Here's the hummingbird wing. It actually outperforms all the other model wings, but they also measured negative drag at really low angles of attack. And what's going on with negative drag? Well, that actually suggests that there's perpetual motion, right? You start to actuate it, you get thrust. That's weird. That would be wonderful. Patent it, you will get rich. But it shows the problem with these type of measurements. And so they had the same problem with another setup, of which they also published results, which is actually a very widely cited paper, very influential in the field. But if you draw this line here around 0, you find that minimum drag is again negative. It's really difficult to measure low drag values. It is. Measuring lift, not that big a deal. So I worked for years on improving the setup that was generally used in the field to actually get accurate measurements and precisely to measure the drag accurately. And that worked out. I'm not going to show you all the details. There will be a paper in the near future. But these are the polars measured for all these 13 species. And you can see they're quite similar. So hummingbirds, there is a difference between wings, but if you look at polars, the differences are not that big. Actually, there are some interesting differences I cannot talk about, but for sure we got non-zero or non-negative drag values. We carefully compared them with literature values for flat plates, etc., and my previous measurements, which I'll show later on. And so if you do them well, you can get reasonable drag values that are actually accurate. So we were also able to look at the flows. This is particle image velocimetry at different wing stations at 45 degrees angles of attack. So the wing is at this angle of attack. And for all these wings, we find this leading edge vortex, this strong vortex core. And whenever you see a little bit of white, that's where a measurement was not, we were not able to make a good measurement. So we don't want to show it. It wouldn't be fair to interpret this result here. But here it's accurate, and here as well. So this shows you, and then the reason why it's so difficult to measure close to the surface is because of the scatter of the surface. So you always have to be careful with analysis. But it shows all these wings, even though the species are quite different, the results for the flows are quite similar. So we also did this for model wings, and this is for an aspect ratio of 4. And you can see this really nice leading edge vortex attached to the wing. And what's interesting about this, so this is a model wing. It has an aspect ratio which is very typical for hummingbirds, around 4. It's roughly on average 3.9. And what happens if we increase the aspect ratio, so the R over C value, what happens with the flow? There were some measurements in the past, but they were just force measurements and not flow measurements, and the force measurements were not accurate. I will not go into all the details, but this is a really interesting result I want to share. So what I found is that here, indeed, I get a stably attached leading edge vortex, but here you actually get much more variation. And this is time average over 20 snapshots. There's a lot of variation because it's unsteady. And I can show you that by showing the non-average results, and to be precise, the circulation of the vortex. So it's the vortex lift for the experts here. So if you look at the vortex lift, and you start here near the center of rotation, and you move outward, what you see is, indeed, we get a lot of lift. These are lift coefficients beyond 2, right? And up to 3, really high values. And a wonderful stable leading edge vortex. But then, around a value of roughly 3 or 4, there is some sort of crisis because the average value plummets and actually the standard deviation increases a lot. The vortex becomes unstable. So having an aspect ratio that's much bigger than 4 can get you into trouble with the stability of this vortex. And so you get some vortex shedding. If we now go back to our graph and plot this result, we can actually see that the majority of the animals on average don't have aspect ratios larger than this value, and a lot of them have lower ones, and there are some differences. For example, this is of course an albatross, and there's some dragonflies. But what I found for the intermediate aspect ratios, actually the flow would not be that separated compared to the aspect ratio 10. So it mostly illustrates why you don't have extreme aspect ratios, and shows that this number and this type of experiment can really give some insight. Here's another dot, and this is actually a rotating seed, an auto-rotating seed. So it's not only animals that fly, of course, also plant seeds, and they're actually the only flying embryos I know. So they're fully developed, ready to grow when they land. So let's get back. We found, for insects, we actually found that indeed, through the literature, people have found this stable leading edge vortex. That's where it was first discovered. Then for bats, my old graduate student, master student to be precise, who went on for a PhD in Lund, discovered the stable leading edge vortex for bats. So bats generated leading edge vortex. And then there's some work by Warwick et al. From 2009. And for hummingbirds, they also discovered, like freely flying hummingbirds, a stable leading edge vortex. And then later on, Florian Muris, who also discovered the leading edge vortex for the bat, discovered it also for flycatchers. So indeed, all these animals can generate a leading edge vortex, but how about this seed? Back in 2006, it was kind of my hobby project. I really love playing around with seeds, like everyone. And I really want to find it out. So what I did is I actually built a robo seed using RoboFly. And I measured the flow around the seed, the same method, at 3 different wing stations. And indeed, you get this really strong leading edge vortex. It's really strong. And here's a 3D flow visualization using 3-dimensional PIV. And I did it for 3 different species and compared it. And in each every case, I found this leading edge vortex. And I was really happy because I'm an aerodynamicist by training. By now I'm also a biologist. Back then I was really much more an aerodynamicist. It's like, yeah, wow, we got results, great. But these are model wings. And so if you get into literature, if you try to publish as an engineer, then you get sensible questions from biologists and saying, well, this is a model, how about the real thing? So prove that. So this is a CT scan, and I can show you what they worry about. So this is a CT scan I made of maple seed. And if you look at the shape, it's much more complex, of course, than this simple plastic plate I used. And the comments I got was like, well, the roughness. Well, being an aerodynamicist, I know that because our Reynolds number is about 1,000, I don't need to worry about turbulence that much. But it wasn't like there was a lot of literature on it or there was a lot of proof, so I had to prove it. So I built a setup for a freely flying maple seed to see if they actually generate a leading edge vortex with that. And so there was no other way for me to influence it. There's no robot whatsoever. It's just flying here in a laser sheet, and that's coming from here. And I filmed it with a high-speed camera, and this is the result. So especially when the wing is pointing towards you, you can see the flow over, and right now you could have seen the vortex but now again, you see a very strong vortex. So for this really flying seed, and as soon as the wing is like this, you can see the vortex. It indeed generates a leading edge vortex. Only near the tip, where it merges with the tip vortex, it becomes a bit more unstable. But near the root, it's really stable, and I repeated these experiments for 32 random seeds that I got from a tree. So, and they all had this vortex. So indeed, LEVs are a convergent solution for high lift in animal and plant flight. And it can give some inspiration for design. Here's the vortex again. And basically, if you look, I didn't make any of my design myself, but auto-rotation is really important. And one example that not everyone might like, but it's actually one of the biggest applications, is this smart bomb. It's auto-rotating, there's a camera, and as soon as the bomb is getting close to the ground, the field of view becomes narrower and narrower, and it is a helpful way for this device to work. Perhaps a nicer application, one that I'm really excited about, is this monocopter by Ulrich et al. And it's a really wonderful helicopter because it's super simple, and it cannot only fly up and down, but also horizontally, actually, by using an unstable mode that these seats have. So it's a pretty clever design, and it's worthwhile looking it up on the internet. So if we look at the inspiration for design, yes, maple seeds form really nice inspiration for effective parachutes and simple helicopters. And now we can get back to key biological questions, and the reason why is because there are other ways to generate this leading edge vortex. And one way is to sweep the wings backward, like a jet fighter. And then you also get a leading edge vortex. This is a result published by Fiedler et al. In Science. And they said, you know, the Swifts generate this vortex to generate a lot of lift, to boost their lift. But what was interesting, they did make wonderful flow visualizations, but didn't measure force. So, and actually I was thinking about it and comparing their results with mine, and I got results like these for the insects. And basically the vortex structure is really different. The difference is that there's a really prominent vortex here near the center of rotation, and here actually near the root there's no vortex. This is more like an extended tip vortex. So is there really more lift? We don't know. But one way to think about it is you can also look at these wings and you notice, wow, a big change in wing area. That's significant. Maybe it's a way for reducing drag, and that was kind of my hypothesis together with a colleague when we wrote a commentary. And one of the reasons to be really excited about these Swifts, not only because they can morph so well, they are really, they're really special animals. They eat, they roost, and they even mate up in the air. So they do almost everything in the air. So if there's one bird that's really aerodynamic and should care about energy, it's a Swift. So, and the way I look upon a Swift as an aerodynamicist is, well, I would like to get rid of the drag, so I get rid of the body. And then I join the wings and I can look at the morphing, because I have to simplify the problem. It's really important to simplify the problem, because otherwise it's too difficult to study. So here we have this wing with different sweeps. I freeze-dried them, I glued them together in different positions, 5 different positions actually for 15 Swift wings, and I made careful measurements of lift and drag with a specially designed setup in a wind tunnel. And I measured the lift and drag for different angles of attack in this wind tunnel, and the flow is coming towards you, right? At different speeds, from 5 meters per second to 30 meters per second, at different G loadings from 0 to 6G, to make really careful measurements. And you might be surprised, like with all the enthusiasm about morphing wings, that back in 2006 or 2005, when I did the measurements, actually nobody had measured the effect of wing morphing on the performance of a bird wing before. So all the experiments out there were with fully extended wings at 1 speed. That's it. No different G loadings, so deforming of the wing or whatsoever, and no different positions like this. And that was just for gliding. You know, like flapping is even more complicated. So, well, here are the force polars. Horizontally I plot drag, vertically I plot lift. The angle of attack changes like this from -6 to 30 degrees. And we can now look at the effect of a morphing wing. What's really neat about it is if you have all these different wing shapes which you can choose from, then actually you have a much bigger enveloping polar. So your overall performance becomes much bigger, much better. And if we look at the leading edge vortex, indeed, we found this vortex also in our experiments for real bird wings. And we found it here, actually, for the swept-back wings, because red, that's the swept-back wing like this. But what you notice is actually the lift is not that high. The lift is just 0.8, whereas previous diagrams that I showed you, the lift was around 1.8. So it's much lower, and if we fully extend the wings, actually we get more lift. So there's a difference between leading-edge vortices generated by swept-back wings versus revolving wings. And that's something that's important to remember whenever you decide to study them. And then we can also look at the drag. Well, if you look at the drag, you see that the swept-back wings actually have less drag. So because they end up here, whereas the fully extended wings are here. So the drag coefficients for the swept-back wings are lower. So indeed, swept-back wings generate less drag. But how does this change with wing area? Because this is, these are the force coefficients. And not only the shape changes of the wing, but also the surface area. And if you include the effect of surface area, you actually see that everything is amplified. So the difference in lift is a factor 2, and the difference in drag is a factor 2. And this shows that morphing wings really help to reduce drag or increase lift. So that's wonderful. And now we would like to know, what does this help the Swift? Because we have all these values, these lift and drag values, but the Swift doesn't care about that. Swift has other objectives, for example, flying energy efficient. I'll show one proxy for that. So we have the lift and drag value for the wing, but the Swift is not a wing. A Swift is a wing with a body. So we had to get the body back. Here's the body. Fortunately, my colleagues in Lund actually did experiments on the body, and when I found out, I actually had done all the experiments on the wing, so we combined everything and had like a wonderful model that enabled us to look at the flight performance of Swifts. And here we look at glide ratio, which is a number that tells you how far you can glide, starting at a certain height. So for example, 1 kilometer height, how far can you glide? If that number is 10, you can glide 10 kilometers forward. So the bigger that number, the better. And this is the maximum glide number for fully extended wings as a function of glide speed, because the Swift could choose a different angle of attack at each and every speed. Well, we just looked at for which angle do you get the maximum performance at that speed, and that's what we plotted. So this is really the best it can do. And then we looked at how that changes with wing shape, so with sweeping backward. And then you can actually see that fully extended wings do much better at low speeds, and swept-back wings do much better at high speeds. And there's a crossover in the maxima. So, and that shows you why morphing makes so much sense. So if you fly slow, fully extended wings. If you fly fast, swept-back wings are best. And, well, looking into this, actually, I did another study, which I haven't published yet, but I think is really exciting. I looked at the airflow near the surface of the bird wing. And actually, I'll show you the results for that point, that exact point there, at 10 meters per second. And this is the result. I'm using a stethoscope to listen to the airflow in the boundary layer. Listen. When it's silent, the flow is laminar. When you hear tonal noise, the flow is still laminar, but there's some sort of wave. And I think it's a Tolmin-Zwichting wave, well-known boundary layer instability. But you'll find at some point here, you have broad spectrum noise, so the flow becomes turbulent. So this is transition from laminar to turbulent flow, and it's the first time it's measured on a bird wing. And the reason why is because it's really difficult. This is the only method I know that works. All the traditional engineering methods don't work. For example, using oil on the wing to look where the oil gets swept away, and then you end up with a line that gives the distinction between turbulent and laminar flow. Well, this is the only method that works, and I used it. And so here's a result. So for example, to find out where transition occurs here. I make a photo, and you can see it here, back here. It's actually transition here, right here. And you can also, in the spectrogram, this is the sound analysis I made, you can also see the tonal noise here, right? So that's the tone we were hearing at that specific location. So, but what you can do is by making a lot of photos, you can determine where the transition occurs from laminar to turbulent flow, and you can actually determine how big the area is over the wing where the flow is turbulent, so where the drag is much higher than normal. And the reason why this is interesting is because if you look at the Swift wing and the upper surface, it's actually very rough. This is actually, I amplified this with a factor 10, but still, aerodynamically it's very rough. It's rough compared to the boundary layer thickness. It really influences the airflow. And if you think about it, and think about airfoil design, that's not logical, making a rough wing. And the reason why the wing is rough is because all these feathers overlap and build this wonderful morphing wing. So how does this work out? How does it compare? Well, let's compare it to what we know. We know a lot about airfoil design for aircraft at Reynolds numbers that are roughly a factor 100 higher than for Swift. So if we look at the Wright Flyer, on the upper surface, it had a roughly like a couple of percent of laminar flow, and after that it was completely turbulent. Then as the airfoil design improved, the laminar flow was extended further down on the upper surface, up till the time that NASA actually discovered how to design natural laminar flow airfoils, and they got 60% laminar flow, which was amazing. And the way they did it, carefully shaping their airfoil, really like dust particles make a difference. I've made measurements on these wings and wind tunnels. Dust particles make a difference. So it has to be super smooth. And I just showed you that these bird wings are not smooth at all. So what's going on? So from a few to 60% laminar flow, a big change by just being careful. Well, let's look at how much laminar flow there is on these bird wings. Well, if you look at, like, this is how far we got in engineering at a higher Reynolds numbers. The birds have much more laminar flow, much more laminar flow. So it's in part an effective Reynolds number, but it also is interesting to see this adaptation, and maybe the roughness actually can help in some way. We don't know, but it's worthwhile studying. So it's an exciting result. I just want to show you. And let's get back to how wing sweep improves flight performance. Well, the way it does is by reducing drag, and we can see that there's some adaptations on the wing surface that could be really intricate and interesting that could further explain this. Well, and now let's get back to our inspiration. This is an example of a flying robot inspired by the results. So it actually has a morphing hand wing built up with 4 feathers compared to the 12 feathers of a Swift, the primary feathers of a Swift. So it's very simplified, really simple design, but it can morph using these feathers. And the mechanism is really simple. There's one servo actuator right here, and it pushes with this push rod against the first feather, and all the other feathers just follow. It's a very simple mechanism. And actually, that's a secret. It has to be simple, because this is a really tiny plane. It's just 50 centimeters span, so it's not really big, and it has to have everything on board. Well, a lot of stuff, cameras, batteries, you name it, like a lot of stuff, and it has to fly. So, and to test if it will work, we tested a wind tunnel. So here you see the wind tunnel results on the right, and we found the same effects. And here's like the parallel mechanism, which is really simple. It's completely built out of carbon fiber, weighs just 100 grams, so less than your cell phone. It has a camera on board, everything, morphing wings, and a folding propeller for gliding. And the students that built it were 10 students, bachelor students, who built it for, again, with a budget of 10,000 euro. And they demonstrated it for the media, and it actually flew in wind force 5 to 6, which was really challenging. And this is a video they made of a demo they gave in India, where they presented their micro-air vehicle at a conference. So here it's flying with fully extended wings. And it's really difficult to film like a bird because it's really tiny.
Kijk, gek.
And they're really enthusiastic. That's one of the students. This is some ground video from India. And now it's going to make a barrel roll like this. And then flies with swept wings. So barrel roll with like thin, flimsy feathers, that's really weird, right? But that's what's so exciting about working with students. They do crazy experiments, and this shows that actually building up a wing with flimsy feathers can make the wing really stable. So it's not that bad a design idea, and it's a nice way of testing it. Well, this robot shows that artificial feathers form an effective morphing wing. It's a very simple solution, it works. And I would like to get back, and that's like the last part of my presentation, to key biological questions. And this is some inspiration for everyone, I hope, because I wanted to have some outreach of my research to society and involve the general public. It's a project that I've been doing in 2011. I spent it a whole year, which was a lot of work, and it was based on this single idea. If you take a very simple high-speed camera, you can go into the field and film funny things, like evolution failing or being very successful about being robust. Just depending on how you look at it. So this longhorn beetle provides inspiration for robots that don't break after bumping into something 4 times, because it bumps into something here again. So it's filmed with a very inexpensive camera, and I was thinking about it like, it's actually filmed by one of the participants. This is not my movie. I was thinking about, like, wouldn't it be cool? I have this one camera, but if I can multiply this camera with 30, so that's what I did. Like, this was the idea, 30 cameras, and get one Phantom V710 high-speed camera, which films 7,500 frames per second. I want to have a really big battery pack, but lightweight, so it's super expensive. It can run for 8 hours in the field, have every lens you can imagine, so from 5 times macro to 400 millimeter tele, and with a 2 times tele extender. Put that all into one big package and just give it to people and let them have fun. That was kind of the idea, and I got money for it. So, and also enthusiasm, because when I announced this idea on national radio in the Netherlands and on national TV, I got responses from everywhere. Everyone wanted to participate. There were like, I only had 2 announcements. We got 800 people emailing us, and we said, well, we stopped, right? That's enough. And so in the end, we got 460 people actually put in all the effort to get to become part of the project, and they're actually the people who we trained to use high-speed cameras. And we won an award with this idea. It's the Dutch Academic Year Prize. It gave half of the money, then another part came from the university, and we got some other sponsors. And we burned all this money in 1 year, almost 300,000 euro on outreach, and it's really amazing. I cannot show you all the results, but I'm going to show you some of it, and it's inspiration for biomimetics, I think, and bio-inspired design. These are some photos of participants. I trained 60 of them myself to work with the Phantom V710. And this is one of the movies one of the participants made in his backyard. He got the camera from one day. He has like 13 or 14 of this type of movies, like really beautiful and really amazing. He's an accountant, so, but he just loves photography. That's all. He didn't know how to film at high speed, so I had to come up with a really simple course that explained it, but he was very successful. This is someone else who is really interested in dragonflies, filming really cool behavior. I haven't seen studied before. I'm sure you can get your PhD if you analyze this behavior from beginning to end. Like 8 flapping wings, and in harmony, like this maneuver is made. And it's just really astonishing, I think, and inspirational. And I didn't film it. Someone filmed it and gave it to me as inspiration for my research, and to you, because it's a movie that's online and freely accessible. And if you don't use it commercially, and just give a reference, like I did there, to those persons, to the project, you can use it for your class or whatever. And here's another movie which is really cool, like a somersault, a fly making a somersault for an escape. It's actually something studied by a graduate student I know very well that worked with Michael Dickerson, but they did it in the field. This is actually the nicest movie ever of this behavior. And they studied for fruit fly, and it looked really weird, tumbling flies. Well, this is actually, I'll show it again, because I think it's actually astonishing. It's almost fully controlled. It gets scared, but look how fast it's had everything back under control again. It's an amazing maneuver. So it's really cool, and you know, I didn't film it because I'm too lazy, and most of us are too lazy to go into the field to film some cool stuff. But they had time, and it's just NS1, so it's not a publication, but it's definitely inspiration. And this is a really boring movie. We got many boring movies, of course, and most people think, geese, you know, who cares? And also, this doesn't look well filmed and everything. But I know some cool things about geese. So I was looking for each and every of the 1,600 Phantom movies I got, and more than 1,000 Casio movies. And they're doing weird stuff. This has never been filmed before. What they're doing, actually, and look carefully, they're flying inverted like this. They're photos, but nobody filmed this at high speed before. And they did it, and they didn't even know after I recognized it. So here it's doing it, and it's keeping its head horizontal, right, for the reasons, gaze stabilization, all those things. So, and it's not one, like there's another one who likes it. And you could say, oh, sure, someone can explain this, right? This has to do with more drag or less drag during landing and stuff. It has to do with crosswind. Well, if you look at the literature, there is no result whatsoever that gives evidence of why this behavior makes sense, really. So we could study that if we're interested. I'm interested, so I think it's fun. Yeah, exactly. And the participants. This is a movie made by some of the participants. The project's called Flight Artists, so there were also a lot of artists participating. And imagine having this camera for 2 days. I think the value is around 8,000 euros for 2 days. And you can do whatever you like. That's what they did. This was their idea. And I'm going to show the result, but it shows the setup, the camera, and kind of the way they worked. I wasn't there, they were just doing their thing. I did explain them that that camera is as much worth as a house in the Netherlands, so they had to be careful. If you work for a full year, you get this back. I thought it was really exciting. Seeing them be creative. So the cameraman was part of my class, all the others were people he found to work with. They got free sponsors. She was the number 2 in a dance competition in the Netherlands, and she decided to join as well. So the idea is to dance inspired by insects, but also bio-inspired. This I really like. This is real. They're seeing for the first time because they had just today. They couldn't practice this. They were seeing those images for the first time. And that's the experience. Like I think a high-speed camera is a little bit like a microscope, with the difference that nobody can buy this microscope. It's not a good one. We're very close to the end of my presentation, and I want to show what they actually made. Because this is just the beginning. This is just what they filmed during those 2 days. But they're artists, so they make something incredible out of it that I cannot. So I want to show that. And that's, can the light be dimmed a little bit, like I asked that? Because I want to show the movie they made. I think it's worthwhile looking. And can it be dimmed a little bit? Yeah. It would be nice. No? Oh, yes. Okay. So I guess it's a love story about bumblebees in some way and between humans and everything. It's definitely bio-inspired. I think it's a very nice movie. I really enjoyed watching it, and it kind of like I am really inspired by bumblebees for other reasons than they were, but in the end we had the same feeling, I think. So thank you for your attention, and thank you. I want to thank all these people for helping me out with all the work I did.
So thanks, David, for a truly fantastic way to finish the conference. And we did ask, I think, for biomimetic art, and we got some, I think, and that was really amazing. And for next year's conference, which I really hope will happen, and we'll start planning it now, we would like to invite suggestions for things like this, biomimetic art, design, suggestions for plenary speakers, and other activities that we might do. And I'm really happy and keen to think outside the box. So if people have proposals of how we can make next year's meeting a really exciting and fun event, then please get in touch. So questions for David, please. Everyone's blown away.
So, of course, that was lovely. I got one of those ES FX cameras, whatever, and have had so much fun with it. I wanted to ask you about four wings.
Mm-hmm.
So, are there interactions, aerodynamic interactions, between two pairs of wings that are flapping antiphasically, or even when they're in phase? What sort of interactions do you get?
I think there are some nice papers on that. For example, by Jim Usherwood, together with, I have to think of his name, he's in Germany now. It'll come back, but there's a nice paper showing the interaction, and it's mostly focused on the wake. I don't think there are many studies on like how the interaction could influence, for example, the vortex or something like that, the leading edge vortex. And I think you're referring to something like that here, and that would be really interesting. To be honest, I think that the studies I did are really interesting because they sort of show a mechanism. But again, I would be more excited about it if there were more species studied, for example, dragonflies. But there are also many butterflies where there are a few studies, but not really in that much detail. And it would be interesting to see, like, if you look at the full diversity of insect flight, how general this is. And interaction is one effect, but definitely also with very, very slender wings for butterflies. The vortex will be there because there are some studies that show this, but the details of the structure, etc., have not been quantitatively measured using PIV or anything.
Right. Because an interesting question comes up that although it might have nothing to do with aerodynamics, the limits may be something else in genetics and development, but why have four wings? Why not have six? What do you get by going from 2 to 4 that you don't get by going from 4 to 6?
Well, what I find interesting, like I'm not sure if I can answer that question, but if you talk with biologists, they definitely say that flies are the most advanced flyers. But if you talk with some others, I'm sure that they would also agree that dragonflies are amazing. And they are really a successful species. So I think the question of 2 versus 4 wings, it's not completely solved. And it's really interesting to see such specialization where we know that dragonflies are very agile hunters, very capable flyers. And we also know that flies are amazing flyers. So, there's still some work to be done. And why not 6, right, or more? Yeah. I do think more wings, the way it would help is it would reduce the disk loading. In a way, like you have more wings to carry the weight, but the interaction is always a problem. You get a lot of interaction, more drag. I'm not sure if you would really benefit, unless you have this constraint where your wingspan cannot be very large and you have to carry a lot of weight, like being a bumblebee. So yeah, yeah. So I don't think there's a clear answer. Like if you look at engineering literature, there's no clear answer why. Yeah.
So of course you have 8 wings when they double up to make love. So you need more data like that, I think.
Yeah, I would definitely call that flying. That's an amazing maneuver. If my robots can mate in the air like that and fly together, That would be fantastic.
Is there anything else you want to share with us today, David?
Yeah, all those movies. There are many more. So,
Okay.
yeah, I
Now,
would
question.
like to share
So
more.
you do this comparison focusing on the hummingbird at some point. You had this graph where you talked about this aspect ratio.
Yes.
And you were trying to tell us that there seems to be some, let's say, sweet spot in that ratio because you saw this clustering of hummingbirds. But in some sense, it also looked like a very bimodal distribution. That indeed was very, very concentrated for your hummingbirds. But if you went out to larger wing sizes, it became much more scattered, and the same
Yes.
also when you went to smaller scale. So is it really fair to say that there is some sort of sweet spot for that aspect ratio?
Yeah, yes and no. It very much has to do, I think, with the ecology of all these species and their behavior, the environment in which they have to live. For example, the birds with very slender wings, they are mostly gulls, for example. And so their adaptations are really different. They don't have to do a lot of takeoff and landing. And I think that's where the big difference is. Like if you have to do a lot of slow hovering flight, takeoff and landing, then this vortex is really useful. But it's actually not a very efficient vortex. It generates a lot of drag. So if you want to glide very efficiently, like a Swift, for example, it doesn't make sense to generate this vortex all the time. And I think the results show that nicely. Even the vortices don't even compare for gliding versus flapping flight, but still, it kind of shows a point. So I think that's one big example. And if you think, for example, of a pheasant, another bird with a very unslender wing, and the main purpose of flight is to escape from a fox, right? So taking off steeply and quickly and flying a couple of 100 meters and then landing, that's kind of the main thing. And that's where those birds do have very unslender wings, very powerful muscles to take off and land, but they're not extremely good gliders.
Right.
So I think there's a lot of scatter because of diversity and evolution. The only thing I'm trying to say is, like, if the aspect ratio is really large, it will not really help you with generating a stable vortex. And I also made performance measurements for those spinning wings, which I haven't published yet. And what it shows is that actually, like, if you think about slender wings, right? For example, revolving wings, and you think about helicopter blades, then you start to think about, oh wow, helicopter blades are really slender. So how about all these animal wings that are not slender? Well, I did actually, like, so there's a study where they say that it doesn't matter. That's the study where they have the negative drag values. I made careful drag measurements, and drag is really important for performance because it tells you how much power it costs to lift something. That's really important when you hover. And so if you look at the results that we got, and this is statistically significant, it's actually at the low angles of attack of helicopters, you need very unslender wings. Very slender wings. So aspect ratios of 10 are great, they're awesome. But if you're going to operate at angles of attack of 45 degrees or 35 degrees, where all these animals are when they're maneuvering and everything, then actually those wings are underperforming, and the aspect ratios of hummingbirds are outperforming them. So it really has to do with the angle of attack where you operate. If you generate this leading edge vortex, and then the slenderness does make a difference, even though the literature right now says it doesn't. I hope to publish this new result this year, maybe early next year. But I think it definitely will change the way we think about wing slenderness and flapping flight. Yeah.
Just one comment. There was a paper in 1995 by Gernot Wendler and Jeff Kamai, where they showed that when locusts fly in tandem, depending on the distance between them, they fly with either in-phase coupling or out-of-phase coupling.
Yes. Okay, I know that for dragonflies to be true for sure.
Yeah.
That's where I don't know that paper, but I know it for dragonflies. Yeah. And that has to do with the advance ratio. So how fast are you flying forward? So if you're flying slowly, it's better to flap out of phase. And if you're flying faster, it's better to, like, have a trail falling, something like that. I think there's no real good aerodynamic study that shows in really precise detail for a specific species how this works. I think there are some really nice engineering papers that look at the interaction, but closing that question, I think, hasn't been done really well. So it's worthwhile studying. It's a great remark.
I've got it right here. I'll send it to you.
Thank you. Yes.
Hi, it's a fantastic talk. I'm wondering about your aeroacoustic measurements that you made on the wing. Is that the only? Are you measuring near field? I guess that's really what it is, with a stethoscope. That's the only thing you can measure, I suppose. Although, have you tried to use an audiovisual camera to really see the vortices?
Well, the problem here is that actually in any wind tunnel there's a lot of noise due to turbulence. For example, the boundary layers of the wind tunnel, there's much more turbulence than on the wing, right? So so you don't hear the sound at all. So this wind tunnel was running at 10 meters per second, and it's completely quiet for us. And only when you have the stethoscope really close to the surface and you are in a turbulent flow, then you get these turbulent fluctuations which you can pick up nearby. But far away, using an array, because that's what you're talking about, an acoustic array, which I think is a fantastic tool. I would love to have one. But still, it would not be the right method for this, because there's so much noise around. It's really difficult to pick up this really small amplitude.
So you're really measuring near field?
Yes.
That's
Yes. And actually, I'm not measuring it completely quantitatively. I'm just listening. When is it like turbulent, when it's laminar, when it's tonal? That's it. And that was already a challenge, a lot of work, because it was all like done by hand, all the traversing and everything. Yeah.
Okay, one last question.
Okay.
Thank you very much. Is there some data for the flying fishes?
Yes, there's a wonderful GB paper that recently came out, I think 1 or 2 years ago. It was from a group in Asia. I'm not sure if it was Japan or China. But yeah, and they also looked at the ground effect, because they actually skimmed quite close to the water surface. It's a really good paper. I can recommend it. They actually used real fins of fish. They dried them, preserved them, and I thought they did a pretty good job at doing that. It's really difficult to do that with fish, so it was nice. Yeah.
Okay, thanks again, David. It's fantastic.
Thanks.
So we're going to conclude the event with a reward ceremony. So,
but first we have to gossip a little bit. Okay.